Hello and welcome back to Calculus 1, section 3.9, also known as the cool section. So, we're going to talk about derivatives of exponential and logarithmic functions. Let's talk about exponential first because we already covered that, and then we are going to go and deal with logarithmic functions. So, the derivative of exponential functions. Well, we already know that the derivative of e to the x is e to the x. So that is one of the formulas which, we dealt with before, and we know that it's the only function that exists which has the derivative to be itself. And then we expanded that to include a constant in front, which is just a chain rule, but it's also a very specific chain rule because we can have the more general idea. So what would be the more general idea? It would be if we had any function, not just ax, but maybe ax squared or sine x or tangent x or whatever. So we can actually have any function up there. And if that is the case, the derivative is e to the f of x times, and the chain rule commands the derivative there. So this would be the first one that I want to box, because this is the most general formula that you can get if e to the x is involved, and that is e to the f of x. But what is actually one boss equation for all exponential? Well, exponential function doesn't have to have e in its base. It could be 2 to the sine x. It could be 5 to the tangent square x. So the most general case that you can see or run into is any kind of base raised to a function. So this is the most general case that you can run into. And the formula for this is going to be copy what you see times the derivative of the exponent times ln b, ln of the base. So this would be the most general formula that you can get for exponential functions. Examples for this are very simple. The derivative of e to the sine x is simply e to the sine x times cosine x, because the chain rule of the exponent, and that takes care of the formula on top. But then we also have the bottom formula, which says, well, what if we are trying to find the derivative of 3 raised to the, let's say, tangent x? Well, by the formula, we have to Control C, Control V, right? You copy the entire thing as is, times the derivative of the exponent, and derivative of tangent is For those of you watching this live, just crickets on the other side. No students, it's just crickets. Derivative of tangent is secant squared, thank you. Holy nightmare. And then times the ln of 3. That's ln b, the base. And that's it. So you either know the formulas or you don't. There's nothing else I can do here for you. So you have the most general case of all exponential functions. So far we just dealt with e to the x and e to the ax. Through the chain rule, e to the x squared plus 1. And now we are just going to change that base from e into anything and have the most general formula that you can think of. And that's the part on exponential derivatives. There's nothing else left for exponential. And they're obviously the easiest and oh, it's the time for a story. Few years back, I had a student in Calculus 3 who was really annoyed that at the first exam, most of the functions that they had to differentiate and integrate were e to some kind of function, or e to the x, or something like that. Made a really strong statement in class. Why there's so many e's, and so on. The comment of another student was literally this: dude, shut up. E is easy to differentiate and integrate. And we did not have issues after that. So once you realize that e's, right, the exponential function is the easiest. I mean, can you get anything easier than this? Right? Even x squared goes into 2x. It changes the quadratic into, right, into linear. Yeah, so you are not going to see these. These guys should be your friends, right? If e to the x had a Facebook page, and if I had a Facebook, I'd be friend. No. All right. So now it's time for logs. Logs. I was never much of an artist, but I try. So gold star for Timmy, right? He tried. Didn't get anywhere, but it's okay. What we're going to do, we're going to first start logs from the very beginning, for the first concept ever, because it's a very well-known fact that for some reason you all are terrible people, you discriminate against logs, and that's not nice. So let's try and be civil. And the way we're going to do that is we're going to start from the very beginning and go through everything for logs and then deal with logarithmic differentiation, creating the most powerful differentiation technique known in Galaxy. But let's see. So I have some questions. How much is 2 plus 3? Crickets, as I say. Thank you very much. One person that knew this. Now, if I want to undo addition, how much is 5 minus 2? And how much is 5 minus 3? So I'm able to recover both of these values from 2 plus 3 is 5. And the next challenging question is, how much is 2 times 3? And if I am to undo this, 3, and 6 divided by 3 is 2. So what do I have? I have the very basic operation of adding, and then we define the opposite operation, subtraction, to kind of undo the addition. And then the fast repeated addition, called multiplication, will have division as its operation that would undo it. Now, what is the fast multiplication, fast repeated multiplication? Well, that would be 3 squared is 9. Great. Actually, let's do 2 squared. What's 2 squared? 2 cubed. I can't. 2 cubed is 8. Thank you. Now, what is the cube root of 8? Great. Now, what am I going to do to retrieve 3? Crickets. Swirr, swirr, swirr. The entire classroom, there is 16,000 people in this classroom. Not a single answer on this one. How do I retrieve 3? There was a cricket in here somewhere. What happened? Use the log. Log base 2 of 8 is equal to 3. There is your mathematical operation to complete the puzzle. What is log? It's just another mathematical operation that was so unfortunate to get letters instead of a symbol. And now no one likes it because of that. Because it's different. Because you discriminate. Because you awful people. Do we understand each other? Yeah. No one discriminates against addition or multiplication or squaring. You're all fine with that. And all of a sudden we toss in 3 letters. Everyone's like run for their lives. It's just a mathematical operation. They could have had it as 2 heart 8 equals 3 and you guys would be all over it. Because he has a symbol. Doesn't have letters. What is log? Simply put, log is mathematical operation between 2 numbers to get a third number like anything else. And then each one of these has rules. You put 2 fingers and another 3 fingers and you have 5, right? And then you take 3 away and you have 2, and that's a subtraction. And you have 5 fingers here times 2 is now 10 fingers, right? So these operations, now yeah, the problem is that we can't do log on fingers, so I guess. There's nothing special about log other than the fact that you learn it the last, and then maybe like 3-4 courses in between, other operations that you learned for the first time, and sure, it's the oddball out. But as you can see, you have a placement where it fits in a table of not even mathematics. This is arithmetic, basic computation. So now, with this, looking at that one and that one, we are able to write the most important formula for logs and exponential functions, which is actually the inverse relationship between them. And that is conversion formula. And that one says a to the b equals c converts back and forth between log base a of c is b. This formula is the most important formula of logs. So now I can understand logs. If the question is how much is log base 2 of 16, right? If I don't know how much that is, so I set it equal to x, I can actually convert this using the conversion into 2 to the x equals 16 and create something that we call exponential equation. And this exponential equation is actually very easy because I can write 16 as 2 to the 4th, from where by simple comparison I see that x is equal to 4, which I can bring back and say that log base 2 of 16 is 4. So I take any log under the galaxy, right, under the sun, in the galaxy, and I can convert it. The problem is that we can't compute it in that way very well. So we use a lot of cool techniques, and we have calculators and other things to compute these logs. You can't do this method for anything out there. For instance, log base 3 of 19. Well, you can just cry, because your conversion is 3 to the x equals 19. And if you try to write this, what do you put in this box? Right? Because that would be the answer. Which is the reason why we use calculators for logs. Now, our calculators, in general, most of them, speak only two bases. There is a special base 10. So log base 10 of x is just called log x. And in your calculator, that's the capital LOG button. And the other one is ln x, which is, log base ex, which is called ln x. And that's the capital LN button in your calculator. So most of the calculators out there would have these two. Some more serious calculators will have only one of these two, not both. So you have to get to know your calculator first and see. Now, some calculators will allow for this as well. None of the graphing calculators, but I believe there is one of the TI 30, 30X, 31, whatever the numbers are. One of them I know for a fact it allows you to plug in the base and the number. But since most of the calculators do not allow you to plug this in, you have to go and learn the change of base formula. So that you can plug in log 319 into the calculator. And the change of base says that log base a of b can be worked out as log b divided by log a, if you want to use the log, or ln b over ln a. And that would be the way to plug in your log base 3 of 19 as ln 19 divided by ln 3. Now, as you use your calculator, make sure you close the parenthesis after you type 19. Otherwise, it will be wrong. So make sure you close the parenthesis. I believe I already talked about that you can get these calculators on your phones. If you use garbage iPhone, you can't, but if you use the real phones, then you can. So I have ln 19, close parenthesis, divided by ln 3. Keep 4 decimals, that's civil enough. So 2.6801. And now you understand why you couldn't solve this problem the way you solved the previous problem. Because this unknown exponent for 3 is 2.68014385 and then decimals probably forever. Right? Compute log base 5 of 193. It's just a quick exercise for you. What do you get? So rounded properly to 4 decimals, 3.2699. And that's the computation part for logs. Now we have some cute formulas that we can use to speed up calculation. For instance, log A of A is 1. That's a nice, cute little formula. Why does it work? Well, think of the conversion of this. A to the 1 is equal to A. Well, that's true. Great. Also, log A of 1 is 0. That says log any base of 1 is 0. That's another cute formula for calculating logs. Now think of it. A to the 0 is 1. Yep, that's true if you do the conversion. So now I don't care if this A is 3 or 7 or 50. Now you might say, yeah, but what if A is 0? You're not allowed to put A is equal to 0. Now you're going to go, why? And I say, because log function. Let's take a look. So you know how I had earlier 2 plus 3 is 5? Well, what I can do is I can replace the 2 with x and I have x plus 3 and call it a function, right? Or I had 2 times 3 is equal to 6. Well, I can replace, let's say, 3 with x and have 2x, and that's also a function. And I can go on in that fact, right, like that. So, to make a function out of logs, I just need to go log base a of x. And then let's say this a is 2. And there you go. Logarithmic function. None of this that I have here is a function. It's just calculations. Just like learning 2 plus 3 is 5. All of this. Log is mathematical operation. It's not a function. Just like plus is not a function. It's operation. So log is a way to compute. Put 2 numbers into the log and a third number comes out. So when you involve x, then becomes a function, then you get the graph, domain, range, and all of the bells and whistles. So what is the graph for log? The graph for log is this, going through 1. What is the domain for log? It's 0 to positive infinity. And what is the range? It's negative infinity to positive infinity. Observe that the 0 is not included in the domain because there is a vertical asymptote at x equals 0. Do you see now that you can't plug in a 0 there? Right? It doesn't work. X equals 0 doesn't work. All right. Log base 0. Good. Yes. I agree. Whatever he said. Now, what am I going to do with logs? Well, what you need to know, and I mentioned this on day 1 in the review, is those 3 formulas for expanding / compressing logs. Here they are. Log any base of xy is log base ax plus log base ay. Log any base of x over y is log base ax minus log base ay. And the third one log a x to the power p is p log a of x. This is something that you really need to know. We're still in pre-calc, clearly. We're not doing anything. Expand. Let's do ln. It's just a is e, so all of these logs become ln if a is e. So expand ln of x cubed y divided by square root of z. This is the standard problem from your pre-Calculus 1 course, and probably almost everyone was going, why? Give me some time, right? Why is coming up? We just need to do this mechanics here. What do I have? I have this main division. That breaks this into ln of the top minus ln of root z using rule number 2 over here. That if you have division of two factors, you just write into two separate logs with minus in. Now if you look at the first one, it's a product. So that's ln x cubed plus ln y minus ln root z. So now I used rule number 1 to break up the first ln into two ln's. And finally, let's use the rule 3 to kick all of the exponents p in front of ln. So I have 3 ln x plus ln y minus 1/2 ln z. If you want to be cool in calculus, you have to be able to do this mentally without writing anything down. So as soon as I write the problem, you give me the last line without writing anything down. That's what I am recommending. Let's go another one. Expand. Ln of x squared minus 1 cubed divided by, let's go with the 5th root of x cubed plus 1. So we can do this in few steps. First off, there is a division which will break into two ln's, and then the 3 goes in front of the first ln, so we can do a little bit of work right off the bat. But now the parenthesis here factors, and this one also factors, which will allow us to break this even further. We don't have to, but since we can, why not? So that's ln of x minus 1 x plus 1 minus 1/5 ln, and this is x plus 1 times x squared minus x plus 1. And now we use the addition to break these apart. So 3 ln x minus 1 plus 3 ln x plus 1. That 3 has to distribute. And now this one also distributes. So minus 1/5 ln x plus 1 and minus 1/5. Right, this minus distributes. Ln of x squared plus 1. X squared minus x plus 1. There we go. And now you see that this term and this term are like terms. It's 3 minus 1/5. So that's 14/5. So 3 ln x minus 1 plus 14/5 ln x plus 1 minus 1/5 ln of x squared minus x plus 1 is 14. So that's the story of logs. There's not that much to it. Now 5 formulas plus those 2 cheap formulas, and that's that. So log is just a way to compute with unfortunate name, as I said before. You have the connection to exponential function as the inverse of exponential function. Basic computation, when things works out, goes quick. Crazier numbers through change of base formula have their own place in decimals. 2 cute formulas to quickly compute things. If you see, let's say, ln e, well, that's equal to 1, because ln is just a lazy notation for log base c, and then when you have base c and number e, then a is equal to a, easy. And then we replace the number with the argument with x, create a function. We have all the specs and stuff like that. And then finally we get into these expansion formulas. So expansion formulas, and we expand these to practice a little bit. Now those same formulas are used to compress, and you use those to solve logarithmic equations in your pre-calc 1. But you really haven't used expansion at all, because there's nothing to do with expansion in pre-calc 1. Compression solves equations and expansion doesn't. So you probably had few examples on the homework, and that was it. So that's the story of logs. And I hope you see that there's really not that much to it. So review that. Now let's consider a problem. Say you want to take the derivative of, I don't know, x cubed plus x minus 9, everything times cosine x divided by the cube root of x to the 5 plus 3. Oh, x cubed, sorry, to the 6th power. That's what I wanted. Sounds good? So what do we have? What type of rules and things in this particular problem? What do we have here? Quotient rule, chain rule? That's it. More? What else do we have? The simplest way to say is everything, because you do have a product rule here, right? And then you have the chain here and the chain here, and this is a quotient. So yeah, go ahead, turn this notebook sideways, and I'll see you in like 20, 30 minutes, right, to work this one out. Or you can just look at this and tell me the answer in factored form right away, without writing anything down. Just dictate the answer. Wouldn't that be cool? Shall we try that one? Let's see how that answer works. So what would be the derivative of this? I'm going to just write out the final factored answer. That's it, without any work in between. So the answer should be x cubed plus x minus 9, everything to the 6th power, times cosine x divided by cube root of x to the 5 plus 3, times, and now here comes the other part. So this one is going to be 18x squared plus 6 divided by x cubed plus x minus 9 plus the let me see. So this one is tangent x minus 1/3 of 5x to the 4th divided by x to the 5 plus 3. There you go. That's the derivative. You had two chain rules, product rule and the quotient rule. And I just skipped all of that and just wrote the answer to the whole problem. It can be done for everything we did so far, completely wiping out chapter 3 off of the book. None of that stuff. Forget about the product, chain, quotient, everything that we did so far. You gotta know the formulas that I wrote on the expansion. So this did freak out my professor in Calc 2, as he was writing something and I'm just dictating derivative as he's writing. Because really you don't have to do anything else other than learn a few really cute rules. So let's see how we take these derivatives or anything we did so far using what we call logarithmic differentiation. The stuff that I'm going to write in between is very long, right? But there is a very simple pattern that you learn, and then derivatives become a joke. So we start by writing that y is equal to x cubed plus x minus 9 to the 6th power times cosine x divided by 3x to the 5 plus 3. And what I'm going to do is I'm going to apply ln to both sides. This is called logarithmic differentiation. When you have logarithmic differentiation, you apply ln. And before I do any derivatives, I am going to use my formulas to expand everything. So I will have ln y is equal to 6 ln of x cubed plus x minus 9 plus ln of cosine x minus 1/3 ln of x to the 5 plus 3. I did 0 calculus so far. All I did is I defined that the whole problem that I want to is equal to function y, and I apply ln on both sides, and I use the expansion formula. Now, I am supposed to take the derivative. Well, we don't know how to take derivative of ln functions yet, right? So that's really cool stuff. Here is what we have to learn. First off, the most basic derivative is of just ln x. And that's just 1 over x. So that's the most basic one. And then the next step higher, which is the one that we actually need to do everything, is that the derivative of ln of f of x. And this is where $1 million is. You copy f of x as is in denominator, and you put its derivative on top. That is my secret weapon. That's my secret weapon. Do you see the cosine x? Do you see the ln of cosine x? Do you see how ln cosine x, that's f of x, goes in denominator? That's the cosine. Derivative of that is sine. Oh, derivative of cosine is negative sine. I have that sign wrong. It's minus tangent x. So, for each one of these, you see that I copy this in denominator, take its derivative on top, multiply by 6, multiply by 1/3. It goes like this. The logarithmic formulas are the ones that destroy these product rules and quotient rules and chain rules. They are the ones that, because look what it did. Over here, do you see that you have a chain rule here? And you see what the formula, what ln did? Took this 6 and put it as a coefficient. You copy that one when you take derivative of this. It's no longer chain rule. And the same thing with the cube root. Used to be exponent of 1/3. Logs allow you to kick that in front, and it's no longer a chain rule. You have a multiplication here for product rule, and logs allow you to write them as addition. It's no longer product rule. This is how powerful this logarithmic differentiation is. It's insane how powerful it is. Once I learned that one, it was clear that, you know, the rest of the stuff is completely unnecessary, because you have this method. And you can mentally take this derivative without writing anything down, as long as you are able to do this, which is expansion from pre-calc 1, in your head. And just go term by term. So let's go. Let's do the problem now. What have I done so far? I have a crazy problem. I define it as equal to y. I apply ln to both sides. And I use the 3 expansion formulas to expand everything. Now it's time to take the derivative. So what I'm going to do is I'm going to put d dx in front. And hello, implicit differentiation. On the left-hand side, what is the derivative of y, ln y? It is clearly 1 over y. dy dx, right? Because we took the derivative of y in respect to x. Equal to, and now I have these 3 derivatives following the bigger formula. Copy 6, take the denominator, copy it as is, put its derivative on top, plus take denominator as is, take its derivative on top, minus 1/3, take denominator as is, put its derivative on top. Do you see that this is already what I have? Now you see that I have the problem, the original problem in front, multiplied by everything. That's your 1 over y going to the other side to get dy dx alone. You see 1 over y there? Well, that 1 over y on the left becomes y times everything on the right. That's the reason why I copied the problem as is. So now, what is dy dx? It is y times, right, as the y goes to the other side. Now this 6 distributes into 18x squared plus 6 divided by x cubed plus x plus 9. No, minus 9, right? Minus tangent x minus, you can call this 5/3 if you want to, x to the 4th over x to the 5 plus 3. All I need to do is to write what y is to have the final derivative. But trust me, writing these steps just slows me down, because we are supposed to be looking at the problem and just writing down the answer immediately. So what do I have? I have x cubed plus x minus 9 times to the 6th power times cosine x divided by cube root of x to the 5 plus 3 times all this mess, 18x squared plus 6 divided by x cubed plus x minus 9 minus tangent x minus 5/3 x to the 4th over x to the 5. Next time, when someone tells you, what do you know? Right? Instead of punching it in the face, you just tell them, okay, take this derivative. Let me show you what I know. I can take this derivative mentally, right? In one shot, while they're still stuck on trying to spell derivative. I know. That's the answer. Now let's do much simpler problem. You know, something that we enjoyed earlier in a course. So let's say, you know, what was the derivative of, as we were learning, let's say product rule, of x squared cosine x? As simple as that. You can write out the answer immediately, but let's practice the steps in between. So first step is y equals x squared cosine x, and then we ln both sides. Then we have ln y is equal to expansion 2 ln x plus ln cosine x. Then we apply implicit derivative everywhere. The left hand side is always 1 over y dy dx, and the right hand side is 2 over x. Right? We know that the derivative of ln x is 1 over x. We learned that. Plus, copy the denominator cosine x, the derivative on top, sine x. So I have dy dx is equal to original function x squared cosine x times 2 over x minus tangent x. Factored form, everything is ready for you to set it equal to 0 and continue your chapter 4 stuff. Now, can we get this answer here mentally just by looking at this? And the answer is yes. I'm going to just talk of what I do in my head as I do these derivatives. All right, so I have any derivative to take. The one that I'm looking at right now, what is the answer? Well, the answer is always multiply the entire function times the multiplication breaks this into two parts. The first part is x squared. There will be a 2 in front because ln jumps in front of the ln. So that's 2 ln x, so 2 1 over x. And then plus, because it's multiplication, the next one is cosine x. That goes in denominator, its derivative on top. And there you go. I can immediately fix this in my head to be this, obviously, but then I've seen students achieve this within Calc 1 while they're working on Calc 1. And it's extremely powerful, as you can see, way to take the derivatives. Now, please don't waste your time with it if you are not good with this. So, if you have issues with expansion, then take care of that issue, taking your time and lots of practice, and then go and try to work these things out. But don't waste your time trying to do the homework for this without knowing those expansion rules, because you can't. You can't. No one can. You must be able to decompose this, expand it using the logs, and then you can kick in and deal with the rest. Let's take a look at the derivative of tangent x. Can we use logarithmic differentiation for this one? Yeah, we can. I'm going to rewrite this as d dx, or sine over cosine. So now my y is equal to sine x over cosine x, and then I have my ln on both sides. I'll use different red. OCD. There we go. So when I expand this, it's ln y equal to ln sine x plus ln cosine x. And when I, that's a minus, yes, thank you, minus. The derivative in respect to x, on the left hand side, 1 over y dy dx is equal to, put the sine in denominator, its derivative on top, minus put the cosine in denominator, its derivative on top. So I have dy dx equal to tangent x, that's the y that goes on the other side, times, and now what I have here, cosine over sine is cotangent x, plus sine over cosine is tangent x. What's tangent times cotangent? 1. Because tangent is sine over cosine and cotangent is cosine over sine, and they all cancel. So it's just 1. So you have 1 plus tangent squared. Isn't that secant squared? Yeah, the first day we had the trig identity. You will never be able to find something in mathematics that you do a different way and get a different answer. That doesn't exist. Everything in mathematics fits perfectly, no matter which way you solve the problem. You can do this problem with the limit, you can do it with the quotient rule, you can do it with logarithmic differentiation. No matter what you do, you will always get secant squared x. If you're not getting secant squared x, A, you're either wrong, or B, you are not seeing some aspect of it. It didn't look good here at all. It didn't look good because you know that tangent is supposed to produce one single term answer, and you are about to get two terms, right? It didn't look good there. But as soon as you see what those two terms are, and you recall the Pythagorean identity, 1 plus tangent squared is equal to secant squared, everything falls into the where it should be. All right. What else? The only tricky ones with logarithmic differentiation where you have to think, and I did get few of these wrong in my own time, is if there is e to the x involved. Remember that e to the x and ln cancel because they're inverses. So the rules of, you know, the copy the function in denominator and its derivative on top, they don't apply for e to the x only. So if I have to take the derivative of one of the good old product rules, like x cubed e to the x, let's say, using logarithmic differentiation here, I mean, it's possible, but it's not as pleasant as the previous stuff because, again, ln and e annihilate each other. But it's doable if you're careful. So y is equal to x cubed e to the x, and then we apply ln to both sides. And at this point, we have ln y is equal to 3 ln x plus ln of e to the x. And this ln e to the x becomes x. So when you simplify that, you get 3 ln x plus x. And now when you take the derivative, we have good old 1 over y dy dx because of the chain rule is equal to, on the other side, 3 over x plus 1 because the derivative of x is 1. So we don't get to use the ln way of taking derivatives because this term here did not have ln because it canceled, right, with e. So you just need to be a little bit careful with those guys. Other than that, we're good. So x cubed e to the x times 3 over x plus 1. Now, we don't like this 3 over x. So steal 1x from x cubed and multiply it in. So it becomes x squared e to the x. To have 3 plus x in the parentheses. It's much better answer. Equal to 0, blah, blah, blah. Chapter 4 continues from here on. Now, can I do this with a product rule? Yeah, that's what we learned. This is the product rule question. Your exam will say, use the product rule to solve. So, you do what? Copy the first times derivative of the second plus copy the second times derivative of the first. What can you kick out? Well, x squared e to the x, right? What's left? X plus 3. Now you're going to argue that my ln way is much longer and much more work. No, you're wrong. My ln method will write this answer by looking at this without writing anything. That's my ln way, okay? And if you practice, you will get to that level, right? There is a Padawan learner, then, right, Jedi. Jedi Knight, Jedi Master, right? And then you become a Force Ghost at the end. So, Ascension, right? So, there are levels. Right now, Padawan, right? That's it. The first level. So, now, another thing to understand is, guys, when you have a toolkit, in a toolkit, you have a hammer and you have a sledgehammer. If you are going to put up a painting on the wall and you have a little, 1.5 inch nail, if you are really careful and strong, sledgehammer of 40 pounds will do, which is what we did over here. The problem is that when you have to break a concrete slab and all you have is a little hammer, it's going to take hours, right? Ding, 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 right? Or the sledgehammer hits it once, right from here directly into the answer, and call it a day. So right tool for the right situation. It's cool to know product rule, quotient rule, chain rule, and all of these other things because they do come in handy. There is really no need to write all of this out if you can just product rule it in 2 steps and be done. But good luck with the upper example, right? With the product rule, quotient rule, chain rule, and everything else in the pile. That's what logarithmic differentiation is for. But technically, going back to any problem we did, log differentiation takes care of everything so far. What would be our application? Obviously, find the equation of the tangent line, yada, 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 right? And there you have it. So just the question is, what method are you using to find the derivative? That's the only question I have. What method? Is it basic, chain rule, product rule, quotient rule, logarithmic, implicit, right? The tangent line problem is always the same. You will use one of those techniques to find the derivative. The rest is plug the point in a derivative, plug the point in the original function, plug everything into y equal mx plus b, get your b, and you're done. Should we do one of those? Just to refresh? Because we are going to spend a long time next week, next Saturday, working with those only. So maybe we can skip. Let's take 2-3 minutes. Deal with the 310, the inverse trig, derivatives of inverse trig, and call it a day. See you all in about 2-3 minutes. Bye.